what makes materials magnetic? All right, let's begin. So in the previous video, we talked about the electrons and the electron spins. So if you were to chop up a magnet over and over again, essentially you end up with an atom, and the atom has spinning electrons, and it's the spinning electrons that have these magnetic dipole moments. Right? So if you, let's say, have an electron that's spinning this way, we can say the dipole moment is going this way. So we have a north side and a south side. But as we learned in chemistry, for every up spin, we can also have a down spin. So if the electron is spinning in the opposite direction, the dipole moment just simply gets reversed. So we have a north side on the bottom and a south side on the top. Okay, and that'll pop up later in the notes of why the paired spins are important to us. But here we have the idea of, okay, so if every object has electrons, they must have these magnetic dipole moments. Therefore, shouldn't all objects have the ability to become magnetic? Okay, so let's go into that. Now, uh, if we have these dipole moments, let's take a look at what these dipole moments look like for a true magnet. So for a true magnet, you have these dipole moments and they are all aligned. Okay, so you have these dipole moments that are all aligned. And so if I were to draw like a physical box around this, essentially you have a south side here. Remember, the B field vectors always come um, into the south and out of the north. So we were to continue it this way, right? It will look like this. So here we have a north side and a south side. So essentially you have a magnet. But this is for, this instance is for when the moments are all aligned. But what if the dipole moments are not aligned, right? And so for every left, you have a right. For every down, you have an up, okay? And you have all of these scattered moments. Well, here, the dipole moments all kind of cancel out each other. And so we have a not magnetic material. And so the B field is zero, essentially, the net B field. Now, different materials behave differently after these circumstances. So most materials, right, if it's not a magnet, it's going to look like this. But really, really cool things happen under the presence of a B field or a magnetic field. So let's go over the first type of material. These are called ferromagnetic. Oops, that M should not be capitalized. So ferromagnetic, in terms of our root words, ferro or ferrous, that means iron. So on the periodic table, iron is Fe, and it comes from this root word. And the reason why we call it ferromagnetic is because iron is one of the materials that can easily become magnetic. So here I have a nail. This nail is not magnetic at all. If I were to put this next to a metallic object, we wouldn't have that magnetic attraction. However, if I were to introduce a magnet to this, okay, it's very is attracted, right? So this magnet is attracted to this iron. But the cool thing that's happening in this presence here is that this magnet is actually aligning all of the magnetic domains so that it essentially is becoming one continuous magnet. So it kind of looks something like this. Let's say the iron bar looks like this, right? All of its domains are scattered, okay, not magnetic at all. But if I were to introduce a magnetic field, or essentially a magnet, to this iron bar, right? I'm going to draw the magnet over here in red, right? Because we saw that there, right? If I have all of these magnetic domains here, okay, and this is the magnetic B field over here, what essentially happens is before the domains were all scattered, but under the influence of this magnetic field, they all become aligned. And thus, this nail essentially becomes a temporary magnet. And for ferromagnetic materials, that effect lasts for quite a while. So after I take off the magnet there, I could actually use this to attract other materials and it'll become magnetic itself. All right, the other type of material is the paramagnetic materials. Paramagnetic materials. All right, paramagnetic. So paramagnetic materials, oftentimes they are They are not magnetic at all, right? And some common examples that we'll see is aluminum. We use aluminum a lot in our demonstrations. Um, and the other kind is gold. We don't really use gold for our demos here for various reasons. But the idea here is that going back to those paired electrons, right? If we have an electron that spins up and an electron spins down, right? What if you had a free floating electron? So this free floating electron is unpaired, therefore it has its own magnetic dipole moment. And so if you have this free floating electron and that's like its dipole moment isn't being canceled out under the influence of a magnetic field, the free floating electrons could essentially, right? So these are my magnetic domains all not lined up. But if I have a magnetic field that's introduced, because I have some free floating electrons, what this B field will do is it will line up the domains. Okay, and this is a temporary effect. It's a very temporary effect. It's a difference between a ferromagnetic and paramagnetic. It's the paramagnetic. It's very short-lived. Right, under the influence of a magnetic field, it'll become a temporary magnetic. But as soon as you remove that magnetic field, it's gone. No longer a magnet. All right, that leads us into our final discussion. Right, so the formula. So those are all the concepts. The ability for a magnet, for a material to become magnetized, we use the Greek letter mu. So mu is what we call the magnetic permeability. Okay, so the definition of magnetic permeability is it describes a substance or object to form magnetic fields. I'm just going to leave it as B. All right. Now, on your formula sheet, there is a constant called mu naught. And this is your permeability. Okay, so the ability to have a B field be created of free space. So essentially a vacuum. So if you have like a free space where there's nothing around, what is the ability for that thing to become or to have its own B field? And that number is, so you don't have to have this memorized because it is given to you on your formula sheet, is 4 pi times 10 to the negative 7, and the units are Newton per area squared. And it's a constant. And this was derived from through different experiments. Now, the important thing about this is a very, very, very low number. And that tells us that free space doesn't have the ability to like turn other things into magnetic materials, right? It's in it itself. It's not a magnet. It's very, very small. And so to describe the ability for a object to sustain this magnetic B field, we call that the relative permeability. And it is a ratio. And you'll see this with a subscript R, and it is equal to mu. So the object's permeability divided by the vacuum's permeability, or the permeability of free space. Okay, and so if mu r is really close to 1, right? So if the permeability is close to the vacuum, that means that the object is not magnetic. Okay, or it's basically like a paramagnetic material, meaning that it's in itself just like the vacuum. However, if the number is not close to 1, then you have a material that can essentially have its own magnetic field be created. All right, I think that's it.